Good morning, ladies and gentlemen. Today is our lecture number 16 and the topic is compensation of transmission lines. Now, before we come to compensation, let us see what is the meaning of rotating var generator. We have already talked about static var generator, SVS or SVC. As the name indicates, rotating, it is dynamic. Anything that is in rotation is dynamism. So, it is also called dynamic compensator as is given here. Now, it is a synchronous motor. I am sure all of you have done machine course in your undergraduate, running at no load and having excitation adjustable over a wide range. This is the beauty of synchronous machine. Though it runs on a constant speed, the control is tremendous because of excitation, field control, and you can have under excited motor, over excited motor, normally excited motor or generator. It feeds whatever watts are required. If you want positive watts, well, it is the line is under over excited conditions and feeds the negative watts when it is under excited, depending on the need requirement. A machine thus running is called synchronous condenser, synchronous compensator, dynamic compensator. There are several names given in the literature. That Miller's book I was referring last time, please do read it in 82, that is John Wiley, reactive power control and management. Now, here is a circuit diagram given on the next slide. This is a rotating var generator. This is synchronous motor. This is the real control here, adjustable excitation, and this is XS, your old friend, synchronous reactance, assuming R 0. In most of the time in electrical engineering, we assume resistance to be 0, which is a fairly good approximation or assumption. The current IC is being fed into the motor, and hence JQC goes into the system, into the line. VR kV is the voltage here, which is supposed to be controlled and kept within very strict narrow range, the band, which I have repeated some 100 times, 0.95 per unit to 1.05 per unit. Now, since motor draws negligible real power from bus bars, the real power drawn is almost 0. EG and VR are nearly in phase. This EG as well as this VR are nearly in phase, and hence I can write an equation for IC VR minus EG 0 degree as a phase angle, root 3 times JX. Why root 3? These voltages are line voltages. X is so much kilo amp. Why kilo amp? Because the voltages are in kV. You have to respect units like anything, otherwise the whole thing can go wrong if your units are wrong. And there where the 50% of the mistakes in electrical engineering are caused because of wrong units. Remaining 50% are caused by root 3. Root 3 is a very dangerous thing. You forget it and finished, your whole electrical engineering is gone. So, JQC, once you know IC, you know the formula VI conjugate. So, since IC is a different direction, we change minus and conjugate VR root 3 phase, that is why 3 times phase. Substitute the value of IC here from here, and hence we get this. Now, conjugate means the J becomes minus J, there is no other angle there. So, only thing what can happen is J becomes minus J, that is angle 90 becomes minus 90 degree. J is an operator which rotates a phasor by 90 degrees. Another operator you must be recalling is symmetrical components alpha, which rotates an angle by 120 degrees. That is symmetrical component. Now, here when you simplify, root 3 will cancel this 3, this minus will become plus, okay. And since this j has gone upstairs, so there is a minus sign, again there will be change. So, this becomes E g minus V r by excess M V A, and if you remove j, it becomes M V A r, and this is a very important equation. And notice the change from this equation to the static VAR system equation. There it was second order, the voltage was second order, here it is first order. Can you tell me one more reason why dynamic compensator is better than static compensator? Because if you recall, there when the voltage sags, you need the help more, and at that time help is less, because it is squared, second order effect. Here what happens, if VR sags, this goes down, but this goes up. So, there is a counterbalance, something goes down, something goes up. So, QC remain fairly good value, it will not reduce drastically, which happens in the static VAR case. So, definitely this is much better mechanism for compensation, especially when there is a too much of a sag, which normally happens in our country, because our UP lines continuously operate at 0.8 per unit, and we call it normal operation, because that has become a normal operation. Similarly, our generating units are derated. What do you mean by derated? That is, the 100 megawatt has never given 100 megawatt, it gives you 80 megawatt. So, we have almost forgotten that this machine is 100 megawatt, for us it is 80 megawatt. Like a government employee comes at 11, goes at 3. So, for his working hours have become from 9 to 5:30, instead of that 11 to 3, and we are used to this. So, same thing is happening in our country everywhere. So, we are happy that 0.8 per unit, we say it is a normal operation, though as you know it should be 0.95. So, we need compensation much more than any other country, because our loads are high, generations are low, systems are badly maintained. From this it is clear, whatever I have said so far is now written in words, that the machine feeds positive VARs into line when Eg is more than VR. That equation is positive. When Eg is more than VR, QC will be positive. Anyone can appreciate this point without any intelligence, because the rest are all positive quantities. When Eg is more than VR, QC is positive, and that is a overexcited case. But if you want negative VARs, when do you want negative VARs? Low load conditions, no load conditions, light load conditions, then Eg should be less than VR. That is the only way you can make that equation negative. That means it has to be under excited case. Okay. VARs are easily and continuously adjustable by adjusting machine excitation, which controls Eg. And excitation control is a well known topic, you might have read it in your undergraduate or some paper. There are several IEEE norms, excitation system, type 1, type 2, type 3. I do not know how many of you have read, otherwise you can see the IEEE website and go for excitation, and you will find similarly IEEE test systems are there, 14 bus, 30 bus, 57 bus, 101 bus, 1000 bus. This you will need if at all you do a project in electrical engineering. So, you need a test system to try your algorithm, to try your method for testing, right. So, there are 14 bus, 30 bus and so on. So, no problem so far. Let us understand some of the implications or observations of dynamic compensator or synchronous compensator, whatever the name is. RVG, this is rotating var generator. There are several names given by different people, give different names. Can provide both positive and negative vars, which is not possible in static var system. See, I can ask you 2 marks. I will talk about the how you should prepare on Wednesday. So, Wednesday class either we can hold here or we can hold there. It is better to hold here because there so many people keep coming. So, but there will be no class like this. We will talk about the preparation for the exam. Monday I will take a class, it's not Tuesday. I mean. Now, this positive and negative vars from the same compensator, this facility is only there in dynamic compensator. There you have to switch from bank of inductors to bank of capacitors back to bank of inductors. I think you should go to the only place in India where static var system is in place and working is Panki, that is near Kanpur, about 20 kilometers or so. As and when you go to IIT Kanpur, do visit that place. I am sure you won't be able to make a visit officially because we are not able to do it within Delhi. Where is the question of going to Kanpur? That is the only place we have static var system in India because it is very costly. Var injection at a given excitation is less sensitive to changes in VR. This point I have already explained to you 5-10 minutes back, because there is a double effect. As VR decreases, EEG minus VR increases. So, this increase will partially compensate the decrease in VR, with consequent smaller reduction in QC compared to static var controller or static var system or static var compensator. This SVC can be meaning anything. So, this is better. This is what is the next line which I have just spoken. It looks DC is better than SC. DC is dynamic compensator, SC is static compensator. DC does not mean direct current, SC does not mean short circuit. However, there are other considerations. This is one consideration, and other considerations are always in life is money. You are also doing MTech so that you get a better job, you get a brand, IIT degree, so you are more sellable. So, here also anybody will ask me question, sir, it is okay, it works well and there is a voltage compensation. How about money, which will cost me less, as our state electricity boards are all in red because nobody pays, and there is another free electricity, etc., etc. Anyway, we are not going into power reforms here in this class. Installation and maintenance problems are other important issues. If something is static, where is the question of maintenance? Why transformer has a 99% efficiency? Because it is a static device. That is a standard answer to this question, which might have been put to you by several teachers in Viva or selection committees. So, there is straight away there is no friction loss, there is no rotational losses and so on. So, this is a dynamic compensator, means rotation is involved. So, maintenance cost will be more as compared to static cost. Similarly, installation cost will be more in case of synchronous machine. In capacitor and bank of inductors, what is installation cost? Further, we do not know where we need this compensation. Where are the loads? The industry can be anywhere, the load can be anywhere. Now, who is going to go, and even in Delhi, if you ring 10 times, then somebody comes for maintenance within Delhi, when they know that IIT is a big customer, and yet they do not care. And AMC, it's already contract is signed, AMC is annual maintenance contract, money is already paid, and that is why they do not come. But if you tell them you have no AMC, they will come, because then the money is there. For each case, separate money. But once you do in this country, AMC means it is NMC, no maintenance contract. Like your TQM is what? You know TQM? Anybody who knows TQM? Very good. You should know these terms. But in India, it is NQM, no quality management. Not low, NO, no quality. Low quality is still better than no quality. Similarly, in India there is a maintenance problem, and these dynamic compensators can be anywhere. Who is going to maintain them? If something goes wrong, that means compensation is not available. So, that limits their practical use. Large compensation DC is preferred anyway. If you want a big MVARs, I do not think you can go on putting banks of capacitors and inductors. So, there is a limit to which you can go for static VAR compensator. So, if you want real large compensation, then DC is the only choice. Now, that was the leftover from the last class. Now, we start today's topic, control by transformers. The compensation still continues. Now, transformers are there anyway, whether you like it or not. Okay? In any power system, even electronics, even computer, that voltage stabilizer is what? Transformer. So, transformer is there in everything, even that shaver or your lady's hair dryer, because the voltage has to be reduced to certain smaller value. And how do you reduce? Transformer is the only way, only mechanism. So, transformer can also control the voltage to some extent. How? By providing taps. If you do not provide taps, there is no control. Whatever number of turns are there, N1 by N2, all your quantities will get transferred from primary to secondary, from side 1 to side 2. Okay? Because primary and secondary again keeps on changing, it depends from which side you are giving input. So, let us say one low voltage side to high voltage side, because low voltage and high voltage side will not keep on shifting. One will be definitely low voltage side, and other will be definitely high voltage side, unless until you change the transformer. So, from LV or to HV, that ratio is fixed N1 by N2. But if you put taps, then that ratio can be marginally changed. You can't make it double. Then one transformer you make and keep on changing its ratio by providing taps. Taps are just there for marginal adjustment. Say if you have called some people for dinner and for 4 persons, if 5th also comes, it is okay, you can perhaps manage, but 4 more come, then the house lady will have a real problem. She may have to cook all over again. So, that is exactly the same thing is here. If there is a smaller adjustment, it can be done by this transformer. Otherwise, you have to again resort to static VAR compensator or dynamic VAR compensator. Right. So, this is more flexible, more economic. Why economic? Transformer damn thing is already there. Can you tell me where do you put taps? HV side. That is well known, because that is the outer side. Of course, that is what I have been talking for last 5 minutes. It is limited to a narrow range of voltage control. You can't just keep on changing the voltage by tap changing. If range exceeds, judicious use of both SVC oblique DC plus transformer recommended. In fact, judicious use of all the three, not both. Both means I have combined this here. That is why I have written both, otherwise you have to read all the three. What percentage of this, what percentage of that, that depends on a particular problem, particular location, particular requirement. You can't give a general prescription. You have to work out each problem separately. Otherwise, you will never need any CA, any MBA if there is a general prescription for all the problems, all financial problems. No audit is required, even medical. So, otherwise there will be one book, cold, take one thing. No, that may be okay for initial till you reach hospital. VR can be raised by simultaneously changing the taps of sending end and receiving end. This is double engine, because taps are there on both the transformers. This is your system. This is 2-bus system. Now, this is Vs and this is Vr. This Vs gets converted to 400 kV. This may be 25 kV or 11 kV. Generation is always at a low kV because of insulation problems, cooling problems, economic problems, and so on. So, when this 25 kV becomes 400 kV, you can as well make it 410 by taps here on sending end. So, that is 410 when gets reduced, it may become 400 here itself. That is what you wanted, and then 400 can be lowered to 11 kV, which is load is there. But suppose this 400 becomes 350 here. So, there is again there are taps here. So, this 350 or 380 can be made 400 back, and you get a 11 kV here. So, that is how these taps are on high voltage side anyway. So, taps will help you both ends. That is what is written here. Simultaneously changing the taps of SE and RE. If you change offline, you can do that, or you can change online. That is called TCUL transformer, tap changing under load. Such tap changes must be made on load and can be done either manually or automatically. If you recall, in olden days when you used to see TV, someone has to go and walk and adjust that knob of voltage stabilizer. Tuck, tuck. Now you don't want to move at all. For every damn thing you have, what's that? Huh? Not automatic regulator. Remote. You don't want anything to do yourself. Perhaps tomorrow you may have a remote bath. Sit here, you will get some water here and take bath. No movement. Anybody doesn't want to move at all. Garage, just put a button on remote, garage will get open. Perhaps next button will bring car out. The third button will put you in the car. And in UK, there are cars where you don't have to even drive. The computer drives it. And there is a screen in which it comes, which road you should take, which is optimum. What is GPS? Global positioning system. Very good. So, he knows it. So, this will tell you which way there is no traffic jam, which way there are less red lights, which is freeway, which is highway, everything. You don't have to do anything, you don't have to think. Computer will think for you. Perhaps you don't need brain. There in West, if you take a 30-cent something, they don't know how much they should give you back if you pay them $1, 70 cents. 70 cents you can't calculate. Anyway, Now, you can do it either manually or automatically. Now, this is the circuit diagram or schematic diagram for transformer control, which I explained you there in a brief way. Now, it is a big diagram here. This is Vs, Is, this is that sending end transformer, which is step up because the generator kV is lower and transmission line needs higher. So, it is 1:2 Ts plus N1. N1 is the original number of turns, Ts is taps, sending end taps. Then this is Zr plus Jx, assuming that it is a short line. Where is multiplied? This is plus. Oh, it should be, you mean multiplied. Sorry. Ts N1. Similarly, it will be Tr N2 is to 1. This is a receiving end. This is I, this is Vr, Ir, this is the load. Tr is less than 1, Ts is more than 1. Transmission line with tape changing transformer at each end. Let Ts and Tr be the fractions of the nominal transformation ratios, that is the tap ratio oblique nominal ratio. A transformer with nominal ratio of 3.3 kV to 11 kV, when tapped to give 12 kV with 3.3 kV input, has Ts is equal to 1.09. So, this much value of Ts is required in case you need 12 kV instead of 11 kV, because 11 kV you will get anyway because of the original turns ratio. But suppose you want higher, as I said, I want 410. So, I can always calculate Ts 410 upon whatever 11, 33, 25 kV depending on the value. So, I will get the value of Ts. So, I must adjust my Ts taps to value of 1.09. Again you refer the figure. This is what is your Kirchhoff voltage law. The voltage at the sending end is Ts N1 Vs, which will be equal to Tr N2 Vr plus drop in Z, which is the series impedance. This equation we already proved it some time back. RPR plus XQR upon VR, it was originally. Now, it is TR into VR. So, what is delta V? The drop Ts N1 Vs minus TR into VR. Is it okay? Taking this on left hand side or keep it there, take this to left hand side and change the sides. Then delta V I am substituting from here and we get this equation. So, is this equation okay for all of you? Ts N1 Vs is equal to Tr N2 Vr plus this delta V. R is resistance, PR is the sending receiving end real power, plus X is reactance, QR is receiving end reactive power, TR N2 VR. In order that the voltage on the HV side of the two transformers be of the same order, if they are of the same order means no drop. Step up transformer and step down transformer, two ends. If the HV side of this and HV side of this are same, that means 400 kV has travelled and still remained 400 kV, it practically means delta V is 0. Tap setting of each transformer with a minimum, we choose TSTR is 1. and hence TR is 1 upon TS. Naturally, if one is more than 1, other has to be less than 1. That is proved from here. And now we substitute here and we get this answer, because I can substitute TR is equal to 1 upon TS in the formula which was there on the last sheet. So, I get this formula. For complete delta V compensation, right hand side should be 1. If this is 1, it means there is no problem of compensation. This is fully compensated. N2 times VR is equal to N1 times Vs, means the same voltage. Is it worth or not? That is a separate issue. It means it involves money, it involves planning, it involves control. So, in practice normally we allow some drop. It is very difficult to have 0 drop. And in fact, now with the power reforms in place, let me tell you what is happening now. The generators, private PPP they call is private power producers, PPP. Not that Bhutto's, what is it, Public Party of Pakistan, what was that? People's Party, not that PPP. This is private power producers. Now there is a competition. Even in Delhi we have 2, BSNL and Tata. That is a separate issue. You have given Tata one side, and so there is no competition. It is only that whole Delhi is divided into 2 private companies. But suppose they can give power to anybody, like you are free to purchase a cell, Airtel, Hutch, BPL or Reliance or whatever. You are free, nobody can force you. Similarly, there are suppose 4 power producers. Now what is happening? They are giving you a raw power without any quality. Quality you decide depending on your need. So the quality has become a responsibility of the consumer. So he will install whatever voltage stabilizer he wants, whatever UPS he wants, whatever harmonics he wants to control or eliminate, it is his headache. They will only use the open access, the transmission line will be already made, and then you can use it. Like if you run a private train or like private planes, private train is not there yet except that Konkan Railway, or there are a couple of more smaller portions, but planes are very much in reality. So jet plane and the Sahara plane also use the same air terminal, same air traffic controllers, and they share the same space. Only thing, there is a coordination done by air traffic controllers. When particular plane will take off, he will give you the green signal, then until then you will be there. Similarly, if you are landing, you will be hovering around Delhi airport till air traffic, he will say, he will announce, the pilot will announce, look, we are 7th in the queue. He may do some biasing, therefore Indian Airlines first, that is a separate issue. But once Indian Airlines also becomes private, even that will go. Then you will say Indian conditions, who gives more money to him, and so on. That let us not go into that detail. So here we get a raw power, and then you are suppose 7 different consumers. Depending on your need, you are a Coca-Cola company man, you are a soap factory man, you are that, what sort of power you need, you will bring up to that quality. So this voltage drop, if it is permitted for you, you will use that. Why should you spend money in compensator? So that is what is to be understood now. Now power quality is no more a requirement from generator point of view. It is a consumer's requirement, and that is why the power quality has become a very important field. There are books on power quality. There are subjects on power quality. If possible, you can take it next semester under your open slot or whatever. Examine properly what courses you can take outside center, and take in electing department such courses, power quality, HVDC or facts, or optimization, power system optimization, and so on. Performance of long EHV AC system can be improved by reactive compensation of series or shunt. Now we have started compensation of lines. So far it was compensation at the receiving end. Now we have come to the transmission line. The aim is same. Aim is only 4. We have 4 objective function. It is a multiple objective problem. Like, what is your problem? Get a MTech degree, try to maximize your CGPA, try to minimize your efforts to achieve that CGPA. If you can somehow find out how to do it, then try to get a good job, try to go abroad and try to become IAS or engineering service somewhere. So, it is a multiple objective function. How you do it, depends on your intelligence and your strategy adopted by you. Similarly, here what are my 4 objectives? I want no voltage drop, voltage profile should be flat, I want good power factors at my load, I want higher transmission line efficiency. Please remember example 5.1 where we achieved all, and I want the maximum power transfer. Transmission capability should go up, EV by X sin delta. So, these are all my objective functions as a power system engineer or electric energy system engineer. Now, which one is more important depends on you. You can't have all maximized. There has to be weighting factors W1, W2, W3, W4, and these weighting factors sigma should be 1. This is taught in optimization course, and you can use goal programming, you can use any mixed integer programming, linear programming, non-linear programming, fault tree approach, evolutionary programming, genetic algorithm, ANN, expert systems. There are so many good techniques. Okay. Now, you can have 2 compensation. 2 compensators are possible, series or shunt. There is no third. Okay. If you want to go from here to Madras, there are only 3 ways you can go: by air, by rail, or by surface transport, car, bus. There is no bus anyway from Delhi to Madras. You have to go in steps. Similarly, for compensation, you have only 2 mechanisms. One is series compensation, another is shunt, and third is of course combination. You have done in control system, lead, lag, lead, lag. Same thing. There also compensation is there. That is a different variety. Similarly, filters. You have filters in circuit theory, you have filters in controls, you have filters in drives, and so on. Active filters, passive filters. Series capacitances and shunt reactors are used to reduce artificially the series reactance. They are not actually reduced. Actual transmission line stays the way it is. What you are trying to do? You are artificially trying to reduce the reactance, so that the power transmission capability go up, so that the voltage drop is reduced, so that voltage profile becomes fine, and so on. All these 4 objectives. And you also want to reduce the shunt susceptance of lines, BC. They act as line compensators, both of them, shunt as well as series. You can read this chapter in Wadhwa's book also. You can read this chapter in Hingorani's book. You can read this chapter in our black book also. And there is a very good paper by Kimbark on compensation in 89 or 88 somewhere. I think I have given the reference of that paper in the new book. In some late 80s. That is his last paper, where in footnote it is written, now Professor Kimbark is no more. You must have read his books on stability. He has 3 volumes. Compensation improves the system stability as well. Do not think that compensation, this is another dimension. It is not only voltage control, it will make system more stable. Why? Your voltage will remain high. Even transmission line efficiency improves with compensation, facilitating line energization and reducing temporary and transient over voltages. You must have done the chapter on over voltages as well. switching over voltages, transient over voltages, temporary over voltages. Compensation reduces Z series line, the series impedance of transmission line. This is how you should write in brief, but do not write it in your papers, the teacher may not understand what you are writing, IAS or engineering services or other courses other than mine. So, these three things can read how much? Series impedance of transmission line, Z series line, and voltage drop also reduces. This is used in chemistry. If you have read chemistry, you must have read. If you remember, I should have said. Then precipitation and then gases, H2 they show the upper arrow, and precipitate means down. So, the same arrows you can use. The voltage drop reduced, P max up and constant B down. What is constant B? ABCD, those generalized circuit constants, ABCD constants. B gets reduced. Why B gets reduced? B is practically Z most of the time. Even if it is a long line, it is Z times sin gamma L upon gamma L. Delta V due to series compensation will be this now. This is a famous equation which we have proved by phasor diagram, figure 5.1 perhaps. This IR cosine phi r plus IX sin phi r now becomes XL minus XC. This XC has come because of compensation. So, naturally when this is reduced here, delta V also gets reduced. How much reduction you want depends on how much money you want to pump in. That means, how much compensation you are willing to provide. How much tasty the toast will be, how much butter you are putting, and you should know also which side of the bread to be buttered, right. Select XC in such a way that this is negative. XL minus XC sin phi r is negative and equals, it should not stop here, and equals in magnitude r cosine phi r. Let us bring back that equation on the screen once again. Now, if this quantity is negative, how much negative you want so that it equals this, then what happens? 0. That is your ideal condition, provided you are willing to spend that much money to bring it, make it negative and equal to this quantity. If you can do that, fair enough, you get constant voltage profile. So, delta V will be 0, and this ratio XC upon XL is called compensation factor. 1 mark question, define compensation factor. Do not write stories, just write XC by XL is called compensation. Always answer to the point, and this quality is very useful for lawyers in the court. Judge will get annoyed if you want to waste time, unless until you are one. You already met him once earlier before coming to the court, then there is no problem. But if you haven't met, he will get annoyed if you waste his time. You should be very, even with the boss, talk minimum. Talking more is always harmful. So, compensation factor is defined as XC by XL. Expressed in percentage, then you call percentage compensation, but like a regulation. Percentage regulation is multiplied by 100, you get percentage value. So, if you are asked in examination and numerical find out percentage regulation, you have no business to give answer is 0.48, you say 48% or 0.05, you write 5%. Do not say, sir, it means the same thing, do not cut my marks, no marks would be cut, because you have been asked in percentage regulation, you are not giving percentage regulation. So, you should not give any opportunity to examiner to cut your single mark. The extent of effect of compensation depends on what? These 3 lines are very important. Depends on number of compensators, this is not no, this is number, and location, where you are putting it. The security, this is security problem. This is called placement problem. What is field placing so important? Why captain is so important person? It is he who asks you to stand at a particular place, field placements, so that you get a catch, so that the ball will not cross the boundary. And this is in every game, do not think it is only cricket, in volleyball, in football, hockey, everywhere. So, same is the game in power systems. Where do you want to have compensation? Is it 1/3 of the transmission line, middle of the transmission line, 80% of the transmission line? This is again an optimization problem. You can find an answer by suitably formulating objective function and using a optimization technique, or experience if you have no time, or ad hoc. Like where do you place these guards? You must have seen guards in campus throughout. Somebody must be planning. They are not just going and standing anywhere they like. Every day they have been asked to go and stand somewhere. And circuit arrangements of series capacitors, how you will put those series capacitors, or shunt reactor stations. These are very huge. If you go and see SPS at Punky, they are like any substations. Do not think it is just 1 feet by 1 feet some box. They are huge substations. I think since there is a next class, any difficulty, we will stop here. Any difficulty so far? So, we have done today, we continued with static was over last time. Today we started dynamic compensator, then we came to transformer tap changing, and now we have started line compensation.